All right, so we're going to pick up where we left off on the same slideshow that we were using the last time, where we were talking about our gauges. So last time we talked about how to read our gauges, how to use those gauges to not only measure pressure, but to use those pressure readings to show how certain refrigerants react at certain temperatures or certain pressures, and how those are related. So we're going to move on through this pretty quick. All right, so refrigerant temperature and pressure. Um, we're going to deal with something called a PT chart, or pressure temperature chart, which is something that you can download from Blackboard, or that I should be able to have in a handout in class. But this is something you're going to probably want to keep for a while. Um, we'll reference it quite a bit in class. You're Some people carry one of these in their wallet or something, a smaller version, but once you learn how to use your gauges, it's really kind of obsolete. But still, you're going to want to at least be aware that it exists and how to use it. So, especially for maybe refrigerants that you don't use all the time, some unique for refrigerant in the system. While you're working on that, you're going to want to need that PT chart to see that pressure temperature relationship. So, one of the things that you'll hear me say a lot, all of this is about temperature. It's about heat. Um, a lot of people get caught up in wondering what their pressures should be at a certain, on a certain system. And so the first thing they look at is PSI. And so they go to their gauges and they say, well, how many pounds should I have on suction, or how many pounds should I have on head, um, you know, on this system? Well, the first thing I'm going to ask is, what are your temperatures? Um, how warm is it in the house? How hot is it outside? All of those things are going to factor in to tell you what your pressures should be. But I don't know what refrigerant you have, so without knowing what refrigerant you have, there's no way to know what pressures you should have. So when I started working in this field, I wasn't taught this way. I was kind of taught more of an old school kind of way of just, you do it to this way, and this is the way it is, and this is what you do. And nothing wrong with it. It worked, and we tried to do the best we could with what we had. But the more I learned that pressure is just a relationship of temperature. And so when you handcuff yourself to a point to think that everything has to fall within a certain parameter, um, that's fine as long as it does. So, if you're looking at like the R22 gauges we were looking at earlier, and you're saying, well, I think that they should always be at, 275 pounds, in this case, since that's what that one says. Well, it's great as long as that's what they actually say. But what if they don't? What does that mean? How do you change that? It's not always easy as just adding more refrigerant. That's not the answer to everything, even though some people might think that's the case. So um, we're dealing with we mentioned last time a saturated refrigerant, which means there is a mixture of liquid and vapor at the same time in the system. And so when we get more into the nuts and bolts of what happens inside of the evaporator, what happens inside the condenser, you'll see that's where those saturations happen. That's where those changes of state happen. So in the evaporator and in the condenser, there are latent and sensible changes happening. So remember from the last lesson, those terms you're going to hear me say a lot: latent and sensible. Um, we're actually going to go through it again today because this covers it in a little different way. So the latent is the change of state. The sensible is the change of temperature measured with the thermometer. So both of those are going to be happening in those two components. There are places in the system, like in the compressor, for example, where it doesn't change states. It only changes pressure and temperature. So, um, we'll get into the nuances of that here in probably the next lecture. But for now, what you need to realize is that different refrigerants change states or boil at different temperatures at different pressures. I know that's confusing, but what you're going to have is you're going to have what we call saturation points. You're going to have one in the evaporator and one in the condenser, or one in the low side and one in the high side. So on your low side, you're going to have a low side saturation or a vapor saturation temperature. On your high side, you're going to have a liquid saturation temperature. Both of those are points where liquid meets vapor, essentially. So I always kind of compare it. If I were drawing a picture on the board, I'd probably do this when we're together. If you could imagine looking out across the ocean at the horizon and seeing the point at which the sky meets the water, that would be kind of representative of a saturation point. That's the point which the change of state happens to where you have liquid meeting vapor. Um, so that's going to happen in the low side, and it's also going to happen in the high side. So in the low side, that's where we're going to deal with your evaporator. So the evaporator, as we have kind of already discussed a little bit, is responsible for absorbing the heat or capturing the heat from the space. Usually it's located in the indoor unit, which is going to be maybe inside the house or in a closet or in a crawl space or a basement or an attic, or occasionally outside. But it's going to deal with the inside air. The condenser is going to deal with the outside air. It's going to be outside, most likely. And so your low side temperature is going to have a saturation point to where the refrigerant in those lines changes from um, a liquid vapor mix to 100% vapor. It's the evaporator. So you think about it's evaporating. The refrigerant inside of that coil is constantly is in the process of evaporating, and when it completely becomes 100% vapor, that's a saturation point, right? So that goes from latent to sensible. I know this is confusing, and I know that it's hard to explain on here, but when we get in class, I will drive this home a whole lot better. I hope so. I'm just trying to introduce these concepts to you, so at least you've heard them. So don't sweat it if you don't get this. I know it's hard. Um, all right, so I'm not going to spend a ton of time on refrigeration circuit because that's a whole other thing. So I was kind of heading that direction. I need to slow down. Using the PT chart. So the pressure temperature chart, that's the relationship between the pressure and the temperature. So if you know a pressure, you can find the refrigerant's temperature or the saturation temperature of that refrigerant. So, or in this case, it says if you know the suction pressure, or in this case, that's the low side. The suction pressure would be dealing with the evaporator. So, as I already said, in that evaporator, you're going to have a point to where that refrigerant changes from um, partial liquid to 100% vapor. That point is the saturation point. Your gauges are going to tell you, like when you go back to your picture of your gauges, um, whatever these gauges are reading on your low side, that is your saturation pressure. That's your low side pressure, and then you correspond that with the temperature that it matches up with. So in this case, if it's 25 degrees, that's telling you that this refrigerant at this pressure boils or changes states at 25 degrees at this pressure. Now, if you had a completely different refrigerant at 50 pounds or 49 pounds, let's say you had 134A, under the same pressure, it's going to boil at a different point. So the term boiling isn't what we normally think. We think of boiling meaning it has to be really hot. Um, it's not always the case. Refrigerant can boil at single digits or below zero even at times. So kind of get that out of your head that something has to be hot to boil. Something has to be, it has to have heat added to it in order to boil, but it doesn't necessarily have to be what we would call hot. So, all right, so your PT charts, if you know either, if you know the pressure or the temperature, you can find the other one. And I will hand you out, like I said, I'll hand you a full-blown PT chart, but this actually has a small example of one. If you know the head pressure, you can find the condensing temperature. If you know the condensing temperature, you can find the head pressure. So here's an example of one. This is kind of like what I'll be handing you. So using PT charts for condensing temperature, let's say. So, well, what is condensing temperature? Without getting too far into the refrigeration circuit yet, this is going to be your high side. This is going to be on your high side, but this is all going to be found You'll have negative temperatures all the way up to 100, 200 degrees even maybe. Um, so it'll just tell you the corresponding pressure at that temperature. So you'll notice here that you have a column that is temperature, different degrees. And then you'll also notice that there's a couple of different refrigerants. Now, this you could have 50 different refrigerants on this, and all you have to be concerned with is the temperature column and then the one column of the refrigerant you're dealing with. So if you got all kinds of columns of all kinds of refrigerants, you really don't need to worry about that. You just need to worry about the one that you're dealing with. So in this case, let's say we're dealing with, we already talked about R22, so let's say we're going to deal with 410A, R410A, which is a different refrigerant. So 410A is a newer refrigerant that's found in almost every residential uh, system that's out there. It's in a pink jug. It's a little more environmentally friendly, ozone friendly, especially. So R22 is actually in the process of being uh, completely phased out. They're not actually making anymore, so there is still some out there, but once it's gone, it's gone. So it's on its way out. 410A has been here for probably the last 15 to 20 years, but now it's becoming you know, basically the only thing in the residential game at this point. So that's mainly what you'll be working with. But in this example, let's say that we have a 110 degree, um, let's say let's start with the pressure. So let's say we're looking at our gauges and we have a 375 psi G on our high side gauge. Well, what does that mean? Well, that means you have 112 degree saturation temperature on your high side. Vice versa, let's say I'm looking at my gauges and I'm saying, okay, I wonder what they should say. And because I understand refrigeration and I understand, how the system works and all that, I come up with the conclusion that this system should be running on the high side at about 100 degrees. So then I would just look over and say, okay, well, what pressure should it be at 100? Well, it should be about 318 of this. Now, what if it's 100 degrees of R22? 196. So that's the biggest difference between, at least for the technician, between these refrigerants is when R22 switched over to 410A, it was a huge switch because the pressures were so much different. We went running like a 70-pound low side pressure and a 200-pound high side pressure to running 130 pounds on the low side and maybe 400 pounds on the high, which to you may not seem like anything. It may not make any sense at all, but for people who had done this for years and years and years and years and years, and they had just went by the theory of, well, I just put my gauges on this many pounds and that's what it's supposed to read. When they had to switch gears and go to a different pressure, it was the same concept and the temperatures were all the same, but because it was a different pressure, people just freaked out. And they were thinking, oh man, these things are going to blow up and, they're dangerous and the jugs of refrigerant are just going to explode when it gets hot and, all this kind of craziness. And, none of that happened. It's a good refrigerant. There's nothing wrong with it. But if you understand the theory of it, that it's more about temperature than it is about pressure, that all that you're really worried about is the temperature that's going on inside of that particular component in the system. And then all that the chart tells you is whatever the corresponding pressure would be with that. So um, a lot of people kind of start out backwards, I think, and I started that way. And you worry about the pressure and you say, well, what should my pressure be? Um, when you understand the theory of what's actually going on, I don't really care what the pressure is. Pressure is just a byproduct of temperature because temperature is really what tells me what it's doing. I can't possibly remember all the pressures at every temperature for every refrigerant that's out there because there's, you know, my gauges have 60 or 70 refrigerants, and there's probably a lot more than that are being used in systems out there. So there's no way I can remember all that. But if I know theory and I know at this many degrees, my gauges should read this many degrees. Okay, well, I don't care what the pressure is. I just need to make sure that I'm on the right column, I'm reading the right refrigerant, and that my temperature's right. And as long as the temperature's right, I don't really care what the pressure is. So stop. Don't train yourself to chase pressures. Train yourself to know what the temperature should be, and then to verify what it is. That's something you'll hear me say a lot. If you put your gauges on a system to find out what it should read, you've already messed up. Uh, electricity is the same way. Your tools are only as good as you are. So you can have the most expensive set of gauges, the most expensive meters, the best tools ever. But if you expect those tools to understand what you don't, you're going to be in a lot of trouble and you're going to make a lot of mistakes. You need to know before you ever put a set of gauges or a meter or anything like that on a system and you're going to take a reading before you ever put it on there. You should have a really good idea of what it should read. And so all that you're doing is verifying that it's doing what you think it should do. If I were to come up to you before you ever put anything on and I say, before you do that, because I will do this a lot, and I say, before you do that, what's it going to read when you put it on there? And you're like, I don't know. Then you have no business putting it on there. Because the point of the gauges is to verify what you already know it should be or what you think it should be. So you have to be smarter than the tools, or if not, you're both, they're just pieces of metal and plastic. So I'm not going to beat that dead horse too long. I'm just going to move on. We'll go over that in class more, and we'll see that a lot. So don't sweat it if you're confused. It's fine. I've always say I try to throw a lot of things out there. I throw a lot of things at you, and I confuse you, on every turn. But I always try to put the pieces back together. So I'm just presenting a lot of things to you, and then when you see it again in lab, at least you're familiar with it. So if you're going through this and you're like, I don't know what he's talking about, I have no clue, that's fine. It's perfectly fine. Just keep following along, take good notes, study what you can, and we'll tie it all together. So we already talked about this the other day. Maybe a better graphic of it: temperature versus BTUs, sensible versus latent. Um, we looked at a chart that was similar to this. Well, okay, so this is something that I didn't talk about last time, and you're going to hear me say this again later when we start really digging into the refrigeration circuit. So remember this. And I mentioned it a little bit, I think, but this is a better vision of it. Um, Latent heat changes the state of a substance. Latent heat in a system. So I mentioned that the evaporator and the condenser, those are the two things that actually kind of do the work of moving heat. So you have four different components. You have a compressor, an evaporator, a condenser, and then you have what we call some sort of metering device, just a device that meters that refrigerant. And we'll explain what that is exactly a little later on. But you got four. That's your four basic components. So it's compressor, condenser, metering device, evaporator, kind of in that order. And that's your basic refrigeration circuit. Um, the evaporator and the condenser are responsible for. The evaporator is responsible for absorbing heat, and the condenser is responsible for rejecting heat. So both of those undergo both sensible and latent changes in those coils. So if you're thinking about a typical heat and air system like that's at your house, if you have an air handler or some sort of coil, maybe some people call it like an A coil, sort of coil in your house that is where the air is blowing across. That's absorbing the heat from the house. And as I mentioned before, your outside coil, that's your condenser coil in air conditioning, and that's rejecting the heat that was picked up from your house. So both of those, in order to do that, they not only have to have a temperature change. So we've already talked how heat has to travel. How does it travel? Hot to cold, right? Hot to cold is, if in doubt, that's the answer to every question I'll ask, uh, because that's the foundation of it all. So um, that coil has to be colder in order to attract warmer air in your house from it, the heat from your house to it. So if you can imagine, you've got this, let's say it's a triangular shaped or pyramid shaped coil that's in the airstream. And and I'll show you this on the board when we get together. But um, this triangular shaped or whatever shape it is, this coil kind of looks like a radiator. It's got fins on it, and refrigerant flows through it. And as that air passes through it, that the refrigerant inside of that coil is responsible for absorbing as much heat as it can absorb. So what we're trying to do is we're trying to transfer, because remember, energy can't be created or destroyed. So we can't just make cold air. We can't just capture heat and then just bloop, make it disappear, right? We have to um, transfer it from one place to another place and to another place until we finally get it to where we want it. So that coil's job is to absorb the heat from the room. So the heat from the room blows across the coil or is pushed across the coil, and then because it's colder, hot goes to cold, and hot being relative, right? 73 degrees in your house may not seem hot, but that coil has to be colder. Um, just as a general rule, that in air conditioning, that coil is going to be about 35 degrees colder. So that's something that you're going to want to remember, and you're going to hear me say a lot. The indoor coil is going to be, the saturation temperature is going to be about 35 degrees colder than the room temp. So yeah, you're running about a 40-degree coil. Okay, so because it's colder, heat attracts to it, but it still can't capture enough heat just through the fact that it's cold. So what really does the most work is the latent part. So the fact that it's cold, going from 70 to 40, that's 30 to 35 degrees of sensible heat. Sensible does some work, but if you look at this little graphic here, um, sensible heat versus latent heat. Even in this graphic right here, this is ice to water, or yeah, uh, or well, ice to 0 degree ice to 32 degree ice. Only 16 BTUs is all that it takes to get ice from 0 degrees to 32 degrees. But in order to melt that same ice from 32 degree ice to 32 degree water, it takes 144. So you can see right there that the latent change absorbs or rejects a lot more heat than the sensible does. So just the temperature change alone isn't enough to catch the kind of heat that we need to carry. So what are we going to have to do? Well, you have to put those coils through some sort of latent change. So that's why they're the evaporator and the condenser, because in the evaporator there's evaporation happening, the process of liquid refrigerant becoming vapor. So as long as it's undergoing that change, kind of like boiling water on your stove. Once you get it to the point that it starts to boil, that's when it really starts to do the work. You're not really going to, boil eggs or whatever it is you're trying to heat up very fast if you have 211-degree water and you never allow it to boil, because you just can't move enough heat to ever make those, that cook. But once you get it to 212 and you start to boil water, you put heat into that like crazy. Even though the water doesn't change temperature at that point anymore, it stays at 212, it's boiling, and it can absorb so much more heat that way. So we have to make those coils go through um, a latent change inside. The refrigerant inside of them has to go through a latent change, so they have the ability to carry a lot of heat. So then, as a result of that, that heat gets transferred from the air, and as a result, the air going into your room is colder, right? So you got 75-degree air blowing across the coil. You remove a bunch of heat from it, and as a result, the air going into your house may be 55. It's kind of a good operating system, what it would be. So now the air feels cold, and it feels like you've made cold air, but all we did was remove some of the heat from it, and we also removed some of the moisture from it. So we made it more comfortable. We made it more, um, it's not just removing the heat; it's removing the moisture. It's conditioning the air, right? That's why it's called air conditioning. So kind of get out of that. All right, so this is the same graphic we had before, 180 BTUs. So if you heard me say before, it takes 1 BTU to move or to heat 1 pound of water 1 degree Fahrenheit. So if you'll notice here in this graphic, 32 degrees to 212, how many degrees difference is that? I'll do the math. 212 minus 32 is 180. Now, if 1 degree requires 1 BTU per pound, and this is a pound of water, for every pound of water that I'm heating in this example, it takes 1 BTU to heat it up 1 degree. So from 32 to 33, 1 BTU. 33, 34, 1 BTU. I'm going to count these all the way up. No, I'm just kidding. Um, so all the way up to there is 180 BTUs. Um, that's not a lot. Your typical, like even a very small air conditioning system, you're talking, just to compare, you're talking like 12,000 or 24,000 BTUs. That's like a 1,200 square foot house. So that's the kind of heat that we're trying to move. So this is a very minuscule amount, as 180 BTUs. Like a light bulb is probably going to put off that much or more. And then once you get to the point that you're actually boiling, you're vaporizing, 970 BTUs during the latent, right? So the arrow that's climbing up, that's sensible temperature, 1, 2, 3, 4, 5, thermometer, right? Latent heat, flat line, because there's no temperature change, it's only change of state. But man, look at the work you're doing. So right here, you're doing 144 BTUs in the ice, from the freezing and the thawing. And this goes both ways. So when I go from, let's say I had this at 100% vapor, I was all the way over here on the right hand side, and then I cooled it down. Well, what happens when I cool down a vapor? Well, what happens to the air in the room if it's got water vapor in it and it attaches to that pop can? It's going to get colder, right? And once it gets to its saturation point, which is, essentially its boiling point, only going the other direction. When it gets to its saturation point, it's going to start to saturate. It's going to start to turn wet. It's going to start to condense. So if you can imagine another line over here to the right, this one doesn't have that drawn up. But once you get to 100% steam, you could keep heating that up. You could pressurize that, and you could what we call superheat that steam. Power plants do that a lot. So once they bring that back down to the point that it hits its saturation point, it's going to go through a process called what? Condensation, right? Condensing. So condensing, it's going to condense. So as it climbs down and it goes across, it's going to hit the saturation point and it's going to cool down. It's rejecting heat and it's going to cool. That's going to allow it to go from a vapor back to a liquid until it becomes 100% liquid. So you could imagine if you had a pot of water on the stove and you could heat it up to the point that all the water boiled away, and then somehow magically you were able to capture all that steam and cool it down. Well, in essence, if you could do that, all the water would come back once you cooled it down, because it's just going to change states back the other way. Now, obviously, that's not going to happen, but that's, in theory, that's what would happen. This is a sealed system, so refrigerants is going to, it has the ability to do that. So as it cools down, it's rejecting heat, and then once it's completely liquid, then it can cool down all the way until it gets ready to freeze. But most of your work was done during the latent heat, during the change. So the condenser does most of the rejecting of the heat, just like the evaporator does most of the capturing of the heat. The condenser rejects it, and the condenser does most of that work through the condensing process, not through the fact that it's hot or cold, or hotter, or it's, yes, it has to be warmer, but it also has to be going through that change. So that's the thing that really drives it. Because if not, your typical air conditioning system would be humongous. I mean, you wouldn't be able to fit it in your house if you didn't have the latent change. All right, so why is it important? So I went through that again because I know we've already talked about it, but going through it again because it's very important to understand this when we're starting into the refrigeration circuit. Utilizing latent heat is the basis of refrigeration. In the evaporator, liquid refrigerant evaporates. Vaporizing absorbs nearly 1,000 times more heat than just raising the temperature of the refrigerant. Okay? So in the evaporator is going to capture heat, but it has to be going through that process. And when it does that, it has 1,000 times more capacity Remember what BTUs is. BTUs is a quantity, it's an amount, right? So you're thinking about, like, if I were to be able to catch all that heat in a bucket, how big a bucket would I have to have, right? Well, if I can put it through this latent change, the bucket don't have to be nearly as big because it has the ability to hold a lot. So it's not just raising or lowering the temperature, it's going through that change of state that really does the work. Um, in the condenser, refrigerant vapor condenses. Condensing rejects nearly 1,000 times more heat than just lowering the temperature of refrigerant. So in the condenser, you're going to be rejecting heat, which is going to cause that refrigerant to cool off. But the cooling off isn't what does the work, it's the change of state. If you're completely confused right now, that's cool. Take a deep breath, keep following along, because we will bring all this together, trust me. This is brand new. I don't expect any of you all to know this stuff. So just bear with me. Got to get through the pre-work before we can get down to the good stuff. All right, so I said earlier that 1 BTU is about one matchstick, one lit match. So if you could imagine, it takes 144 BTUs to melt 1 pound of water, or 1 pound of 32-degree ice into 32-degree water. But the temperature doesn't change. So once it becomes 100% water, it's still 32 degrees. Now, 32-degree water all the way up to 212 degrees takes 180 of those matches. And this is where the work really starts. 970 BTUs to vaporize that. It has the ability to hold a whole lot more. So another example, and something we may actually demonstrate in class, I don't know. If you could imagine, like, you've got let's say you've got some sort of, I always go back to food, but I love food, so there's that. But let's say you have a bowl of really hot soup or something, and so you're trying to cool this down so you can eat it. And so I don't know if you do this or not, but sometimes if I have a bowl of hot soup, I like to get my food to where I can wolf it down. I like to get it to where I can eat it. I don't like to slurp around on it and waste time like I like to eat. So I may try to cool it down. Well, what's the best way to cool that down? Throw a piece of ice in there, right, or a couple pieces or whatever. Let's say, or maybe you boiled some tea and you just made some iced tea. So it's hot and you're trying to cool it down real quick. So the best thing to do is throw some ice cubes in there. Now, what if you took, let's say you had an ice tray and it had 20 slots in it, and you filled all those up with water, and that water was 32 degrees. And then you had the same amount of ice trays full of ice. Okay, so you took all that ice and you said, I'm going to dump this water in instead because, I think it'll be the same. What do you think would happen if I took, an ice cube tray full of cold water and I dumped it in my soup versus that same amount of ice? Well, for one, the ice is going to stay there longer because it's not going to be dissolved as quick, right? It's got to melt. But because it stays there longer and it takes more energy to actually melt it, it has the ability to capture more heat from the thing I'm trying to remove it from. So that's a perfect example. The water, one little spoonful of cold water wouldn't do anything to that bowl of soup, but a piece of ice in there floating around, it has the ability to stay there longer because it takes more heat to actually get rid of it. So hopefully that helps you see that a little bit better. All right, I'm not going to spend a ton more time on that. All right, so I don't know if I want to get into that right now. Okay, I guess maybe I do. All right, so this is something I'm not going to get into a bunch of time other than just to give you the terms. So when you see them again, you'll at least have some sort of semblance of it. Two terms that we will use a lot are superheat and subcooling, or something is superheated and subcooled. Anything that anything that is cooled to the point that, like, think about the condenser or the condensing water. So you've got the water vapor and it's cooling down to its saturation point, and it cools down all the way to the point that it is no longer any vapor, it's all water. And then you drop it another degree. So back to this little example here. So let's say you got a condensing. Let's assume cool air removes exactly 970 BTUs, which is what it takes to condense all that water back down. So you got 970 BTUs, and at that point you have exactly 212-degree water, but none of it is boiling. It's just at the point of heading the other direction, right? At this point, all the vapor's gone, and now you went from a latent change, and you're getting ready to go back down that slide, and you're going to go to a sensible change, which is measurable with a thermometer. So let's say you remove a little bit more heat. Well, what happens if you remove just a little bit more? Well, that 212-degree water will become subcooled by 1 degree. So it now becomes 211-degree water. Well, 211-degree water, 212-degree water, still hot, right? Well, at this point, that water would be subcooled, which means it is 1 degree or however many degrees below its saturation point, below its condensing point. So it is 100% liquid, and then it's this many degrees past 100% liquid. Does that make sense? Um, it will, because we're going to cover this a lot. A condenser, subcooled liquid refrigerant. So that's where we're really going to talk about that. Same thing with superheat. So superheat is in the vapor side. So if you can imagine, you're heating that water up on the stove, you're getting it to the point that it's boiling, and then you get it to the point that it becomes 100% vapor. At the point that it becomes 100% vapor, if you heated it 1 more degree, that is superheated. So it is 1 degree beyond its saturation point. So hopefully that makes sense a little bit. At least you see that. So when you see those again, at least you'll have some sort of idea as to what they mean. Superheat's going to deal with vapor, superheated vapor, subcooled liquid. Alright, so not spending a ton of time on that. You will see these laws, and we may reference these at times. I'm not going to spend a bunch of time on these. Um, Pascal's law, Dalton's law, and Charles's law. These are different laws that we will use at times. So, like this, for example, Charles's law. Your book talks about this. You could use this to indicate a leak in certain gases. So we use nitrogen to pressure check the system. Um, you could actually use this. Some people think nitrogen doesn't change pressures with temperature, but it actually does. But nitrogen is a gas; it doesn't condense. So it's 100% gas when you put it in the system, but it can change pressures with temperature. So if you put nitrogen in the system, you leave it overnight. So let's say it's 90 degrees in the afternoon when you put it in. You come back the next morning, it's 70 degrees because it's colder outside. Um, how much would you expect the temperature or the pressure to drop, if any? You could use Charles's law to calculate that. So we'll probably reference that again when we get into leak checking, but I'm not going to spend a bunch of time on it. Just want you to know that it's there. So what that really helps you with is it lets you know that there you could think there's a leak because it lost pressure, and in reality, it's just because it got cooler. All right, another thing that you will want to remember: air is a bad thing in a refrigerant system. Air takes up space, and it is what we call a non-condensable, which means it will not condense in a system. So it will just remain as air, and can cause a lot of problems. It increases your pressures, causes things not to work right. So you want to eliminate the introduction of air as much as you can. I'm skipping a lot of this stuff because it's just, in my opinion, not super relevant. Um, okay, this is probably our last little area here, but I do want to cover this. We will cover this more. So you may have heard this term, like a ton. How big is your air conditioner at your house? Well, it's a 2 ton, or it's a 3 ton, or it's a 5 ton, or whatever. So what does that mean? Well, I remember the first time I heard this, and I thought, uh, my dad pastors a church, and at this church they were wanting to put in 2 systems. It's not a huge church, and it's just a little old country church, and they were going to put in air conditioning for the first time. And so this was years ago, before I knew anything about this. And they said they were going to put in a 5 ton system and a 2 ton system. And I thought, man, those are big. And then they said that they were going to get the 2 ton system or the 5 ton system up into the attic. And I thought, there is no way that our ceiling is going to handle that. Little did I know that it weighed maybe 100 pounds. So, it wasn't physically 2 tons. So, what does that mean? Well, um, if air conditioning is the process of moving heat, and BTUs measures a quantity of heat, then 12,000 BTUs is equal to BTUs per hour is equal to 1 ton of refrigeration. Now, what does that mean? Where does that come from? Well, here's where it comes from. So years ago, there was a contest or a whatever, that they were trying to figure out, if they had a ton of ice, how long would it take for it to melt? How much heat would it take for it to melt? And so, people came and they measured, and I think it even talks about this in your book. They measured and they calculated, and scientists were using all sorts of things. And so, what they come up with was that it took 12,000 BTUs per hour, or 288,000 BTUs per day, a 24-hour day, to melt a 2,000 pound, 1 ton piece of ice, in a 24-hour period. So, that was the amount of heat that it required. Uh, that's where the term ton came from. So, our systems are sized in tons and half tons, and you'll notice, and I'll show you this on your systems. It's usually indicated in the model number somehow, like kind of coded in the model number, that there will be some number that is either divisible of 12 or half of 12. So, for example, you may have a system that's a GSZ 36, whatever, AX, some random model number, but the number that I'm looking for when it comes to sizing is that 36. Well, what does 36 tell me? 36 tells me it is 36,000 BTUs. 36,000 divided by 12,000 is 3. That's a 3-ton system. And it could be half of 12, so it can be 18. You don't really have a lot of 12,000 BTU systems out there, but in split systems, residential split systems. But you could have 18,000, 24, 30, 36, 42, 48, and then for some reason it skips 4.5 ton usually and goes straight to 5, which is 60,000. That's kind of the residential spectrum. So residential stuff usually stops at 5 ton, and then beyond that it becomes more commercial. But you could have systems in commercial buildings that are hundreds, if not thousands, of tons. So that stuff gets pretty big. So that's where that comes from. So if you ever wonder what that term was, there you go. So they're breaking it down and they're saying, well, if you remember, the latent heat of fusion was 144 BTUs per pound. Fusion being the freezing and thawing. 1 pound of water at 144 BTUs per pound. So if I have 2,000 pounds of ice in a 24-hour period, do the math. That works out to 288,000 BTUs. So that's how they came up with that. And then you divide that by 24, and that's 12,000. All right, so I'm gonna stop right there. We're not gonna deal with humidity right now. All right, so that's the end of that. I'm gonna have a quiz that goes along with this, so it should be linked in this module. You will complete that quiz, and that will be your ticket to do the lab on this. So this lab, we're going to start getting into refrigerants and all that good stuff. So hopefully you can knock that out pretty quick and move on to the next module. Thank you.